Chapter 7 Assess and Improve Data Quality. Section 7.1 Data Quality Matters. Data quality refers to, the quality of the data. High quality data are well organized and have minimal noise, artifacts, or missing values. Low quality data can lead to mismanagement, confusion, errors, and misinterpretation. The purpose of this chapter is to introduce you to methods to evaluate and improve the quality of your data. Because data are so diverse and have so many origins and applications, there's no single global measure of data quality. Instead, you will need to learn several measures of quality and then mix and match and possibly develop new quantifications to customize the data cleaning pipeline to your specific application and data set. Fortunately, data quality can be improved, at least somewhat, through various transformations, algorithms, and filtering techniques. In this chapter, you will learn several common methods for improving data quality. But when it comes to your data, you will need to decide how to evaluate, clean, and process the data to ensure that it has the highest possible quality before applying statistical analyses. Data quality control is not necessarily the most fun or insightful part of working with data, but it is important, so try to be meticulous, critical, patient, and unbiased when collecting and cleaning data. Performing data cleaning effectively requires statistic knowledge, hands-on experience, a solid understanding of the subject matter, and familiarity with the unique characteristics of the data at hand. Section 7.1.1 Data Quality Influences Data-Driven Decisions. Why is it important to have high-quality data? The reason is that all decisions are based on data. Every decision you make is based on data. Perhaps you disagree, politely I hope, with that claim. Maybe you think that some decisions are based on data while other decisions are based on experience or emotion or gut feelings. But where do those gut feelings come from? They come from data. Those data are your past experiences, stories you heard from other people, or things you've read in books or blogs or saw in a TikTok video. The problem is that these kinds of data are often anecdotes or small sample observations, and the data they provide are not necessarily of high quality. Or perhaps they do not generalize. A one-time experience that was appropriate in one context may be inappropriate in another. The point is that we are constantly making data-based decisions, even if we don't realize that we are making data-based decisions. And so, if we want to make good decisions, we need good data. But getting back to the practical matters of statistics, the purpose of statistics is to help you make decisions based on data. Those decisions might be about supporting an hypothesis in an academic, scientific research study, optimizing a financial investment portfolio, evaluating safety hazards in a factory, or choosing an economic and political strategy that has the potential to affect millions of lives. Regardless of the nature and impact of the decision, the quality of that decision depends in large part on the quality of the data. Garbage in, garbage out, or GIGO. If you start with crappy data, you're going to get crappy results. There is no fancy, super cool, sophisticated data analysis method that can compensate for really bad data. On the other hand, the converse of GIGO is not necessarily true. Having amazing high-quality data does not guarantee amazing results. Amazing results depend on many factors, including a good hypothesis, well-conducted experiment, accurate measurements, and appropriate statistical analyses. Therefore, high-quality data is necessary but not sufficient for high-quality decision-making. Do not be embarrassed by low-quality or insufficient data. The data are the data, and you should embrace the reality of imperfect data. In fact, One of the most important database decisions is I need more data before making a decision. Section 7.2 Data Cleaning Phases. There are 4 different time windows in which you have the opportunity to control and improve the quality of your data. Figure 7.1 provides a conceptual overview of those time windows, and the text below provides more description. The take-home message is that the earlier you invest in generating high-quality data, the larger the dividends in terms of quality. Figure 7.1 shows a conceptual graph illustrating the positive, that's black circles in the left axis, and negative, that would be the gray circles in the right axis, impacts of data quality control in the research timeline. So the x-axis conceptually represents time. There are 4 time points indicated: before data collection, during data collection, after data collection, during data analyses. The left axis is labeled QC, quality control, positive impact, and the right axis is labeled risk of bias. There are 2 lines on this plot. One is a gray line corresponding to the right axis, which is the risk of bias, and it increases from left to right, so from before data collection to during data analyses, illustrating the concept that the risk of bias increases as you perform data quality control later in the research timeline. The other line is black circles connected by a thin line that corresponds to the left axis of the positive impact of data quality control, and that line generally decreases over the time period of research. Back to the text. Before getting data. The best way to have high-quality data is to collect high-quality data, which means engaging preemptive strategies before data acquisition begins. Now, this is possible only if you are involved in data acquisition or generation. Basically, your goal is to try to anticipate problems that might arise during data processing and analyses and adapt the data acquisition to minimize the risk of those problems. You will be able to anticipate problems with data analyses as you gain more experience working with data, but here are 2 tips to help you get started. First, familiarize yourself with scientific publications, technical reports, blog posts, YouTube videos, and so on, where similar kinds of analyses have been performed on similar kinds of data. Consider the limitations or difficulties they faced and determine what you could do to avoid those limitations. Second, consult with experienced people who have worked with these kinds of data or analyses and ask what they would have done differently or what they wish they had known before the data were acquired. One of the best ways to ensure high-quality experiments that produce high-quality data is to conduct a pilot study to collect and analyze a small amount of data. Hopefully, unanticipated problems will be revealed during the pilot study, and the research can be optimized accordingly. During data collection. Data are acquired in a myriad of ways, but some types of experiments allow the researcher to monitor the data as they are being collected. If you have this luxury, inspect the data in real time to check for artifacts, sensor miscalibrations, or other issues that could reduce data quality. If possible, pause data collection and try to fix the problem. Never assume that subsequent data cleaning or analysis strategies will magically fix low-quality data. After data collection. Post-data collection cleaning comprises 2 possible strategies: data transformation and data rejection. You learned about data transformations in the previous chapter. Data rejection involves removing data that can negatively impact the final results, perhaps because the data are excessively noisy, or perhaps because the data contain extreme values or outliers. Although some statistical analyses are robust to outliers, many commonly used analyses are sensitive even to a single excessive data point. You will learn outlier identification and rejection strategies later in this chapter. During data analysis. This is the worst time to perform data quality control because it brings the highest risk of biasing the results. Biases can be introduced intentionally or accidentally by selecting or modifying data in a way that increases the chance that a certain statistical result will occur, even if that effect is not really present in the data. How this can happen and how to avoid it is the topic of Chapter 18. To be sure, data cleaning during statistical analyses is sometimes necessary and justified, but you should avoid transforming or selecting data when possible during the analysis stage. Section 7.3, Assessing Data Quality. There are two families of approaches to assess the quality of your data. I separate them below for ease of discussion, but you don't choose only one approach. They complement each other and should both be used when possible. Qualitative quality assessments. Qualitative inspection of your data means visual inspection. It means that you visualize your data in one or several ways and invest several moments of your life staring at your screen. What do you look for when visualizing data for quality assessment? Here are some tips. Tip 1. The range of the data. Check that the numerical values are what you expect them to be. The data shown in Figure 7.2a has suspiciously similar values for the first 20 data points. This could be due to an equipment problem. Another example. If your dataset comprises rental durations from a bike share company, you would expect the data to be in the range of tens of minutes. If the data values are less than 1, then there could be an error, or maybe the data are coded in hours instead of minutes, which is also important to know. This paragraph references Figure 7.2a. Figure 7.2a shows a scatter plot with data index on the x-axis and data value on the y-axis. And you see that the first 20 or 25 or so data points have almost exactly the same value. They are very constrained on the y-axis, and after that, the data are much more distributed. The title of this panel is Unexpected Data Range. Back to the text. Point 2, the shape of the distribution. The shape of the distribution has implications for the types of statistical analyses that are appropriate, as well as transformations you may wish to apply. The distribution in Figure 7.2b doesn't look like any typical analytical distribution, so there might be some data clipping or noise issues. This paragraph refers to Figure 7.2b, which shows a histogram of a non-standard distribution. There is a peak around 1/3 of the way through the x-axis, which has a shoulder going off to the left that never falls down to 0, never tapers down to 0, and it tapers very rapidly off to the right, but the distribution is very strongly right skewed. It is not a distribution that you typically see as derived from analytic functions such as Gaussian distribution or uniform or power law distribution. Back to the text. Point 3, single or multiple groupings. If the data are collected from a homogeneous system, then the data should appear to form a single group. If you see multiple groupings or clusters, then it is possible that the data comprise several distinct groups. You've seen a few examples of these distributions in this book already with multiple peaks. These kinds of distributions warrant further investigation, possibly justifying splitting the data into groups. This paragraph references Figure 7.2c, which shows a histogram that contains two Gaussians. One is further to the left, and the other one is further to the right. The title of this panel is Mixed Data Set. Back to the text. Point 4, outliers. I will have much more to write about outliers later in this chapter, but unusual data values relative to the rest of the distribution are often easily, visually, identifiable. This paragraph references figure 7.2d, which shows a scatter plot of data index on the x-axis and data value on the y-axis. Most of the data are clustered at a relatively low data value, and there are two data points that are much higher than all of the rest, and these are outliers. Back to the text. Quantitative quality assessments. There are several quantitative measures of data quality that can be used. The most useful metrics tend to be application-specific and sometimes dataset-specific. The non-exclusive list below will give you an idea of the kinds of quality assessments that might be relevant. First, sample sizes. Larger samples tend to provide more trustworthy statistical results. This is due to a variety of reasons, including subtle effects might be detectable only with large samples, the impact of noise is reduced, population parameters are more accurately estimated, subgrouping and individual differences analyses are more feasible. Now, keep in mind that larger sample sizes do not trivially lead to higher quality data, but generally speaking, the larger the sample size, the more reliable the results of statistical analyses. There is also a psychological component to this. Larger samples usually take more money, effort, time, and resources to acquire, which probably, hopefully, translates into spending more time thinking critically about the research before it begins. Now, what constitutes a large sample size? N equals 30, 300, 1 million? This is a challenging determination, and I'll have more to say about it in chapter 17. Second point, error rates. This refers to the amount of missing or rejected data. The more data that are removed, the lower the quality of the pre-cleaned data. High error rates may also raise doubts about the quality of the experiment design, equipment, and post-cleaned data. Point 3, data range. The data range refers to the minimum and maximum data values. This characteristic may reveal problems with the data. For example, if you have a dataset on click-through rates for different online advertisements, then a range that includes 100% indicates that something is likely wrong. I seriously doubt that even the most eye-catching website ad would reach a click-through rate of 100%. I mean, come on. Next point. Variance. Variance is a Goldilocks data characteristic. Too little or too much is bad, but just the right amount of variance is optimal. Statistical analyses require some amount of variance. Otherwise, there's nothing to explain. But too much variance can reduce the estimation of statistical parameters and can obscure even real effects. Footnote. There is a fascinating concept in engineering and science called stochastic facilitation, which refers to the idea that some nonlinear systems require stochasticity or noise for optimal function. Back to the text. As discussed in Chapter 4, raw variance can be challenging to compare across variables with different units. However, large variance discrepancies among variables with the same unit may indicate the presence of outliers or corrupted data. End of list. There are other methods for quantitative assessments of data, like correlation matrices, which I'll come back to later in the book. Section 7.4, Improving Data Quality Through Transformations. In some cases, transformations can be used to convert data into a format that is more suitable for analysis. For example, strongly right-tailed data distributions become more Gaussian after the log transform. Many transformations are available, as you learned in the previous chapter. It can be difficult to know which transformations are appropriate for which situations, particularly nonlinear transformations. Indeed, in Chapter 11, you will see an example of the profound impact that transformations can have on the results of statistical analyses. Domain-specific knowledge is useful in deciding whether and how to transform your data. Regardless, it is important to check the distribution of the data before and after each transformation to ensure that the data quality has in fact improved. Section 7.5, What are outliers? An outlier is a data point with a relatively unusual value. What does it mean for a data point to have a relatively unusual value? Relative to what? And what does unusual mean? And who decides whether the value is unusual? Labeling a data value as an outlier entails some subjective and arbitrary decisions, and it is possible that two different people with the same data set would disagree about what should be considered an outlier. Most of the rest of this chapter focuses on various aspects of identifying, interpreting, and dealing with outliers. These pesky little beasts can either be the bane of a statistician's existence or the inspiration for a new line of scientific inquiry. Section 7.5.1, How to Think About Outliers. Let us not fall into the laziness trap of proclaiming all outliers evil, horrible, no good monsters that must be removed without hesitation or remorse. In fact, outliers are a nuanced topic that deserves a deeper treatment than is often given on websites and introductory statistics books and courses. Outlier is actually an umbrella term that encompasses several different and qualitatively distinct phenomena. How you interpret and deal with outliers depends on your assumptions about where they come from and what they mean. Quote, the outlier is an invalid data point, end quote. Invalid data can come from noise, mistakes, sensor malfunction, or other errors. For example, imagine that a researcher is collecting data on the weight of ladybugs measured in different areas of a forest. According to some Google searches, ladybugs weigh approximately 0.02 grams. Perhaps the researcher forgot to press the decimal point key when typing in the weight of one sample, and that ladybug was recorded as weighing 254 grams instead of 0.0254. Now that's clearly an invalid data point and should not be included in statistical analyses. Other invalid data points can arise from intentional human behavior. For example, someone filling in an online survey claims that their birth year is 1852. Some people find this sort of behavior amusing. I don't know. Outliers that fall into this category should be identified and removed. In some cases, it might be feasible to correct the mistake. For example, the ladybug example. But in most cases, the invalid data point should simply be marked for rejection. Quote, the outlier is valid data, but unusual, end quote. Here we have a completely different scenario. The outlier is not due to noise or error, but has a value that is different from most of the other data values. For example, imagine gathering net worth data from every adult male living in the USA with the first name of Jeff. Now, most Jeffs would have a net worth in the range of tens to hundreds of thousands of dollars. But then we have a certain Jeff Bezos whose net worth exceeds $100 billion at the time of this writing. Now, that value is extremely different from that of the other Jeffs, but it's not an invalid data point or the result of a data entry mistake. There are many other less dramatic examples. Flood insurance is much higher on the coast of Texas compared to Utah. Terrorism is low in most countries but high in a small number of countries. A company might make most of their sales on one product and few sales on other products. Most pop music is 2 to 3 minutes long, but some pop songs are over 10 minutes. Gift wrapping paper sales are low most of the year, but extremely high in the week before Christmas. Most credit card transactions are relatively small and in the geographical area of the card holder, but an unusually large charge in a foreign country might be fraudulent, and so on. Such data points are labeled using terms like non-representative, anomalous, extreme, or deviant. These data points are unusual, but they are accurate measures of the world. These kinds of outliers are more difficult to deal with. On the one hand, including them in statistical analyses risks biasing the results. For example, including Bezos's net worth in the average will make it seem like all the other Jeffs are much wealthier than the reality. But on the other hand, valid data should not simply be tossed out of the dataset because they are inconvenient. In fact, throwing out inconvenient data introduces its own biases and is dangerously close to data manipulation or outright fraud. Outliers require decisions. The point here is that unusual data values are not necessarily bad. There is a story behind each outlier. Maybe that story is a simple one like a data entry error or equipment malfunction, or maybe that story is an insightful one like wealth inequality or the impact of climate change on local economies. You need to understand that story to make an informed decision, and that decision will branch into one of two outcomes. Outcome 1, remove outliers. Here, the assumption is that the outliers are invalid data. They do not reflect the system you are interested in. Outcome 2, keep outliers. Here, the assumption is that the outliers are valid data but are unusual. These data values can have a negative impact on statistical characterizations and analyses, and so you have three options for addressing this situation. Option 1, apply a data transformation to shrink the impact of outliers. The log transform, for example, will shrink large data values. Option 2, use analyses that are robust to outliers, like non-parametric statistics or robust weighted regression. Option 3, perform a subgroups analysis, which involves separating the data into groups that have similar characteristics and apply statistical analyses on each group separately. I suppose the main take-home message from this section is that you need to think carefully about outliers. Rejecting data based on being labeled an outlier is certainly justified in many cases, but you should never thoughtlessly remove data. Section 7.6, Identifying Outliers. As I wrote in section 7.3, you can perform qualitative data inspection by visualizing the data and looking for unusual patterns or data points. Specifically with regards to outliers, look for one or a small number of data points that are outside the range of the rest of the data. Figure 7.3 shows an example. Figure 7.3 shows simulated data illustrating two data points that are unusually large relative to the rest of the data. These can be considered outliers. The figure shows a scatter plot with data index on the x-axis ranging from 0 to 100, data value on the y-axis, and we see that most of the data points are between -2 and +2, and there are two data points that have values somewhere around 8. They are visually very obviously different from the rest of the distribution. Back to the text. Although visual qualitative inspection of data is an excellent way to become familiar with your data, there are a few reasons why qualitative identification of outliers is not always the optimal approach. Number 1, visual inspection-based outlier assessment is not scalable. Visual inspection works on a small or univariate dataset. It cannot scale to large, multitudinous, or multivariate datasets. Point 2, qualitative outlier identification increases the risk of subjective bias. Background knowledge that you have about the data might bias you towards labeling a data point as an outlier or as not an outlier. Perhaps you are more likely to label a data point as an outlier if your hypothesis predicts that the mean of the data should be small. Or perhaps your current levels of stress, hunger, tiredness, frustration with your PhD research, or time until lunch break affects your decision to label a data point as an outlier. Point 3. Related to the previous point, decisions about outlier identification might be non-reproducible. That is, what you consider an outlier might be different from what someone else considers an outlier. This means that different people handling the same data might get different results. Now, to be clear, none of these points are fatal flaws, and I would not make the general recommendation that outliers should never be identified based on qualitative means. Indeed, in my research lab, we use visual inspection to identify artifacts in multi-channel neural time series data. But qualitative assessments can be tricky and usually require some domain-specific training. Algorithmic or semi-algorithmic outlier identification strategies should generally be preferred unless there is a clear justification for the qualitative approach. Section 7.6.1, Absolute Threshold Detection. The idea here is simple. Data values are expected to be within a certain range, and data outside that range are considered outliers. Going back to the ladybug weight example, we do not expect ladybugs to weigh more than, say, 0.05 grams, and therefore any point larger than that is flagged as an outlier. The advantage of this method is that it is custom-tailored to each individual dataset, which means that the researcher brings domain-specific knowledge to optimize outlier detection. There are two disadvantages of absolute thresholds. First, people unfamiliar with the experimental methodology might struggle to choose appropriate thresholds. Second, the numerical data values might depend on equipment calibration or settings, which means that appropriate thresholds might be equipment or even dataset specific. Section 7.6.2, the Z-score method. The primary disadvantage of absolute threshold detection methods can be countered using a relative threshold. That's the motivation for Z-score method of outlier detection. Z-scores and data proportions. Before explaining the Z-score method for identifying outliers, I will first explain how Z-scores can be used to characterize the amount of data contained within different Z-score bounds. Figure 7.4 shows the standard Gaussian distribution, which has units of standard deviations, or Z-scores. In a dataset with this distribution, 68.3% of the data are within one standard deviation around the mean. That is, ranging from one standard deviation below the mean to one standard deviation above the mean, so a total of 2 standard deviations. 95.5% of the data are less than 2 standard deviations away from the mean, so 2 standard deviations on each side, thus a total span of 4 standard deviations. And 99.7% of the data are within 3 standard deviations from the mean. I recommend committing these Z proportion pairs to memory. It's useful knowledge to have at your fingertips. This paragraph references figure 7.4, which illustrates the concept that if the data are Gaussian distributed, you can determine the proportion of data within each standard deviation distance away from the mean. You will learn how to convert between standard deviation units and proportion of a distribution in Chapter 10. This figure shows a normal distribution, a Gaussian or bell curve, with standard deviation units on the x-axis ranging from -4 to +4 and 0 in the middle. And then there are 3 horizontal bars indicating the percentage of data that can be expected within 1 standard deviation of the mean, 2 standard deviations, and 3 standard deviations of the mean. So the bar indicating 1 standard deviation of the mean is labeled 68.3%. The next bar shows the 95.5% spanning from -2 to +2 standard deviations, And then we have the bar going from -3 to +3 standard deviations, indicating 99.7% of the data. Back to the text. Armed with this knowledge, we can use z-scores to identify relatively large data values as outliers. The z-score method. The z-score method is very common, perhaps the most common method of identifying outliers. And it is simple. Convert the data to z-scores and consider any data values with a z-score exceeding some threshold to be an outlier. The strength of this method is that it works for myriad datasets, regardless of whether the data are in units of grams, meters, newtons, counts, euros. You get the idea. The z-score method to identify outliers is useful in any dataset that can be transformed into z-scores, which means any numerical dataset. Consider, for example, figure 7.5. The data have been transformed into z-scores, and any data point with a z value over 3.29 is considered an outlier. Why use a z-score threshold of 3.29? This corresponds to a probability value of p less than 0.001 for reasons you will learn about in Chapter 8. For now, suffice it to say that a threshold of around 3 is typical in many applications. This paragraph references figure 7.5, which illustrates the idea of using z-score thresholding to identify outliers. The caption reads, simulated data illustrating a dataset in panel A with an outlier identified using the z-score method in panel B. The horizontal dashed line shows the threshold for labeling data points as outliers. The two panels A and B show the same data. In panel A on the left, we have a scatter plot showing the data with a data value on the y-index ranging from around 5 to around 9. And on the right in panel B, we have exactly the same data, but now transformed into z-score. So the numerical range here is from around -1.2 to around 5. There's a horizontal dashed line at y equals 3.29, and one data point above that line has a z-score of maybe around 4.9, and that data point has an X drawn on top of it, indicating that it is labeled an outlier. Back to the text. This figure also illustrates the subjective nature of outlier identification with a threshold. For example, the data point at approximately index 130 is just barely below the threshold. Had I chosen a slightly lower threshold, or had that data value been slightly higher, it would have been labeled as an outlier. Now, the description I wrote above is for identifying positive outliers. Of course, outliers can also have unusual values to the left of the distribution. Therefore, in practice, the threshold to identify outliers is two-tailed, which we can express as the absolute value of z greater than 3.29. In other words, 3 standard deviations above or below the mean of the distribution. A few comments about the z-score method for identifying outliers. Comment 1. It is exact and reproducible, meaning that anyone, given the same data and the same z-score threshold, will get the same result. Comment 2. Because it relies on z-scoring, the z-score method is relative. This means that the same data value might be labeled as an outlier or not an outlier depending on the rest of the data values. Comment 3. It has one parameter, the threshold, and that entails some subjectivity. Common threshold values are 2.3, 3, and 3.29. If more variability is expected in the data, a threshold of, for example, 5 or maybe 8 might be appropriate. Non-normal data might also require a more extreme threshold, or you can use the modified Z method. Modified Z. In the previous chapter, you learned that the modified Z-score can be used in place of the regular z-score when the median and MAD, median absolute difference, are more appropriate measures of central tendency and dispersion compared to the mean and standard deviation. The same idea holds for identifying outliers. Section 7.6.3, Iterative Z-score Method. One issue with using a relative transformation is that the transformed values depend on other values in the dataset. Imagine a scenario like that illustrated in Figure 7.6. The presence of a few outliers will increase the standard deviation, which shrinks the z-score values for the rest of the data points. And without those outliers, the recalculated z values would be larger. This paragraph refers to Figure 7.6, which shows z values will change after removing outliers. There are two panels, A and B, on the left and the right. Panel A shows some data with an outlier. It's the rightmost data value. We see a scatter plot with data index on the x-axis. The values are somewhere around 6. For most of the values, there's one data point around the middle that has a value of 8.2 or so. And the rightmost data point has an extreme value of somewhere around 10.5. Panel B shows the same data, but z-transformed, calculated before and after removing that large outlier. So we see a scatter plot of the same data, but with a z-transform applied. The range of the values is now -1 to +0.5 for most of the values, but then there are the outliers. There are two sets of data points here, squares and circles. The circles depict the z-transform data without the extreme outlier, the rightmost data point. And you see that the circles and the squares are not entirely overlapping, they are different. In particular, the most remarkable value here, or difference here, is that the smaller outlier towards the center of the data set, which had a value of a little bit above 8 in the raw data, has its z-transformed value go from around 1 to around 2.5, with versus without the extreme outlier. So the idea is that the z values changed because the outlier biased the mean and inflated the standard deviation of the initial z-score calculation. Back to the text. This feature of z-scoring provides the inspiration for the iterative z-score method. Here's how it works. Step 1, implement the z-score method described above. Label any data with z values more extreme than the threshold as outliers. Step 2, recalculate the z-scores, excluding the outliers labeled in Step 1. Mark any new data values that exceed the threshold as outliers. Step 3, repeat Step 2 until there are no more outliers. You can see an example of the procedure in Figure 7.7. Code to implement this method and produce this figure is part of Exercise 1. Figure 7.7 is an illustration of the iterative z-score method for identifying outliers. Each data point is labeled according to the iteration number, and data values are plotted with an X if they are labeled as outliers and removed from the subsequent iteration. This figure shows a scatter plot, but instead of the data points being indicated as, for example, squares or circles, they're indicated using numbers. So we see a bunch of zeros, and then there is one blue data point that has an X instead of a 0, with a value of around 4, indicating that it was excluded at iteration 0, or the first iteration. And then in red, we see numbers 1 in the scatter plot. Those are roughly the same as 0, but slightly different, indicating that the z-score values changed from the first iteration, iteration 0, to the second iteration, which is labeled as iteration 1. And now there is a new data point that was currently rejected in iteration 1 that was not rejected in iteration 0. Back to the text. What do you think about the data point with index 17? This is the data value that was not labeled as an outlier in the first iteration, but it was considered an outlier in the second iteration. In iteration 0, it was not marked as an outlier, but in iteration 1, it became supra-threshold and was removed. Now, this data point does not look unusually large to me. Granted, I set the threshold at z equals 2, which is quite lenient. Still, the key points here are 1, iterative methods with arbitrary thresholds can remove more data than you might think is appropriate, and 2, blindly trusting any algorithm is risky and not recommended. Always inspect your data. This method is useful for datasets that contain a range of outlier values, in particular, quote-unquote, smaller outliers and extremely large outliers, with the latter values biasing the standard deviation in a way that obscures the quote-unquote smaller outliers. The result of this method tends to be more liberal in that data values that are towards the edge but not necessarily extreme might be removed. Iterative z-score outlier detection is actually not so commonly used, but it is useful to know about, and it provides a great opportunity for a challenging coding exercise. Section 7.6.4, Removing data by trimming. Another option for cleaning data and removing outliers is called trimming. The motivation is the same as with the thresholding methods: remove data with excessive values. But the implementation differs in an important aspect. Instead of removing any data that exceed a threshold, the most extreme k points are removed, or alternatively, the k% of the distribution is removed. For example, we can set k equals 2 for each tail, which would mean that the largest 2 positive data points and the largest 2 negative data points are removed. You can already imagine the risk of such an approach. The largest 2 data points might not be outliers, or perhaps there are 3 outliers and 1 is missed by the trimming. This paragraph refers to figure 7.8. This is an illustration of trimming a set number of data points, panel A, or a percentage of the data distribution, panel B. Both panels illustrate a two-tailed trim. So figure 7.8 shows 2 panels, panel A on top and panel B on the bottom. In panel A, we see a scatter plot with around 75 data values, and each data value is indicated using light gray squares. The 2 most negative values and the 2 most positive values are X'd out, and it looks like the 2 positive X'd out values are outliers, and there's 1 negative value that looks like an outlier, and another X'd out value that seems to be pretty comfortably within the range of most of the other data values. Panel B shows a Gaussian distribution, a bell curve, and the regions around -2 to -4 and +2 to +4 are grayed out, indicating that those percentiles of the data distribution would be rejected. Back to the text. To be honest, I am not a fan of this method for the reasons stated above. Nevertheless, it is good to know about, and perhaps you may find this method appropriate for your data. The advantages of data trimming are that it is fast and easy to implement and reproducible by anyone with the same data and k value. Section 7.6.5, Manual, Automatic, and Semi-Automatic Cleaning. An automatic approach to outlier removal involves trusting your algorithm to remove outliers for you, whereas a manual approach involves identifying outliers based on visual inspection. The advantage of the former is its ease and reproducibility, while the advantage of the latter is the expert domain knowledge that the researcher leverages. A semi-automatic approach combines the advantages of both approaches. The idea is to use an algorithm to identify putative outliers without removing them from the data. Then an expert would inspect the data and approve or reject the algorithm's suggestions. Another advantage of the semi-automatic approach is that it ameliorates the scalability problem. A huge amount of data requires a huge amount of time for a human to inspect. But if an algorithm can flag suspicious-looking data, the expert researcher can focus only on the flagged data without having to inspect the entire data set. This approach is frequently used in business and financial data processing. For example, an algorithm may flag a large cash deposit into your bank account for a human specialist to investigate. Section 7.6.6 What happens to rejected outliers? In some cases, it may be feasible simply to remove the outlier from the data as if it never existed. Thus, a 100 sample dataset with 2 outliers would become a 98 sample dataset. But in many cases, complete removal is not the right approach. This is because outliers may occur in one feature and not in others, and it is unfortunate to remove an entire row of data only for an outlier in one column. In other cases, data are paired and must be matched with corresponding rows in other columns or in separate data sets. Therefore, in practice, rejected data can be replaced with NaN. NaN stands for not a number. Mathematically, it's the result of dividing by 0, but it is often used in statistical programs to indicate a data point to ignore in computations. Hybrid methods. Various outlier detection strategies can be mixed and matched. For example, perhaps you would start with an absolute threshold to remove data values that are so egregiously extreme that they must be errors, and then apply the iterative method to identify non-error outliers, but you use the modified Z instead of the regular Z score because the data are non-normally distributed. More generally, optimal outlier detection methods are often application-specific. You should consider the corpus of outlier detection methods as tools from which you select the best ones for the job. Section 7.7 Analysis-based solutions to outliers. Dismissing outliers as if they were poisonous ingredients in your magical data brew can sometimes obliterate meaningful nuances. Sometimes non-representative values are actually valid data points. You want to keep them in the data set, but you do not want them to skew your results. In this case, you can perform one of several analysis methods that are designed to include extreme data values while minimizing their potential outsized impact. Non-parametric analyses. Several statistical methods like t-test, correlation, and ANOVA have non-parametric alternatives that involve either rank transforming the data or testing medians instead of means. These alternatives are robust to outliers because outliers have little impact on the median. However, non-parametric analyses can have reduced sensitivity to detecting subtle effects, in part because meaningful variability is removed while rank transforming. You will learn about these methods in later chapters. Permutation-based tests. Permutation-based statistics involves creating empirical null hypothesis distributions based on randomly reassigning data points to other groups or experiment conditions. In the process, outliers in one condition are randomly assigned to other conditions. And this means that outliers are incorporated into the statistical inference process. You'll learn about permutation-based statistics in Chapter 16. Weighted analyses. If the problem with outliers is that they have an outsized impact on the results, then why not deweight them? Deweighting outliers means to multiply them by a numerical value between 0 and 1 based on their quote-unquote outlier badness. For example, in the data set 1, 2, 3, 40, we might have a weighting vector of 1, 1, 1.1. Now the original data value of 40 enters the analysis as a value of 4. Weighting data values is a good idea in theory, but the implementation can be tricky. For example, how to define the weights. I will write more about this in Chapter 15. Subgroups analysis. If there are many data values that could be labeled as outliers, it is possible that they represent a separate group of individuals that may be qualitatively distinct from the rest of the group. For example, imagine a data set of the gas mileage of 100 cars, 80 of which have miles per gallon in the range of 18 to 25, whereas 20 of them have a miles per gallon in the range of 40 to 60. Those 20 cars may seem like outliers when, in fact, they are electric gas hybrids. Subsequent statistical analyses could be performed separately on the two groups. Section 7.8, Missing Data. Missing data can present significant challenges in statistics and can have a significant impact on the results of your study. Figure 7.9 shows an example of a data set with missing data. Figure 7.9 is a data table with 4 rows and 2 columns labeled time 1 and time 2. We see that there is one missing value in time 2. It is in the 3rd row, 2nd column, and it's indicated with a question mark instead of a numerical value. Back to the text. Data can be missing for several reasons. Dropout. In studies that track the same individuals over time, these are called longitudinal studies, participants can refuse to continue participating in the study, move away, or die. May sound morbid, but it happens in medical studies. These individuals may provide partial data that can be useful for some but not all analyses. Equipment malfunction. Technical problems can cause parts of the data to be irretrievably lost, corrupted, or unusable. Human error. Sometimes data go missing due to honest mistakes. What do you do with missing data? Let us count the ways. In the discussion below, recall that data tables are organized as features in the columns and observations in the rows. One option is row-wise removal. If a row contains at least one missing data value, then remove the entire row. This can be an appropriate strategy for paired data, for example, measuring sports performance before versus after a week-long training course. The assumption is that if there are missing data, then no data from that individual are usable. The second option is analysis-specific row removal. A disadvantage of row-wise removal is that the non-missing data in a row might be valid and usable. Therefore, an alternative is to keep the row in the dataset, but exclude that row only from statistical analyses that require that data point. This method is particularly useful if you have limited data or are performing multiple analyses, at least some of which do not include the feature with missing data. In these cases, the offending data values are replaced with NaN to preserve the dataset size and order. Another option is imputation or replacement. The idea here is to replace missing values with estimated values based on the available data. The average of the extant data values for that feature is often used. For example, the missing data value in figure 7.9 would be 6 2/3, which is the average of the valid data values for time 2. Another option is predictive modeling. This is conceptually the same as imputation, except that a more detailed statistical model is used to predict a missing data value instead of a simple statistical model that predicts that each data value simply takes on its feature average. The complexity of the predictive model can range from simple regression to deep learning artificial neural networks. This approach is advantageous because it provides more plausible estimates of missing data values But fitting the model parameters requires a relatively large amount of data. Thus, this method is feasible only for large data sets. Section 7.9 is the exercises. If you would like to see overviews of the solutions to these exercises, please consult my YouTube channel. End of Chapter 7.